Classic example of new scientific method is physics of orbits. And this new physics is very different, very accurate compared to previous models of our solar system. We'll need to understand forces, acceleration, gravity, mass vs weight, and angular momentum to explain what is happening in our solar system and how planets move. What are fundamental forces? We have gravity. Matter attracts other matters, and this attraction depends on their mass. We have electromagnetism between positive and negative electric charges. Opposite charges attract, like charges repel each other. We have a strong nuclear force, which is very short range but keeps particles in the nucleus. We have weak nuclear force, which is very short range and is responsible for radioactive decay of nucleus. For basic structure of an atom, we have electrons with negative charge and we have nucleus with positive charge. If we take two atoms, when they get closer, electrons have the same charge, so they will repel each other. On the other hand, nucleus has positive charge, so nucleus will attract electrons. So this is attraction. So we have repel and we have attraction. And there are a lot of examples for fundamental forces in everyday. Gravity pulls things towards the earth. Electromagnetism holds solids together, and when one object pushes another object, we have electromagnetism. Air resistance is electromagnetism. Friction is electromagnetic force. Chemical reactions are due to electromagnetic force, and basically everything else. These forces have differences. They work in different scales. For example, if we compare electromagnetic force with gravity, gravity is very weak force, but the main difference is gravity works on very large distance. So electromagnetism is a short-range strong force, but gravity is a long-range weak force. For example, 0.5 gram electrons for electromagnetic force is equivalent to this huge number in gram of Earth. So gravity is really weak force, and we need a lot of matter to have gravity. For force, we have Newton's second law. And according to this law, when we have a force, there is acceleration, there is change in speed. And this acceleration is equal to force divided by mass. So what it means, if we have more force, we have big acceleration. If we have more mass, we have smaller acceleration. So this acceleration is proportional to the force, but it's inversely proportional to the mass. If there is no force, F is 0, so acceleration is 0, so there is no change in speed. It doesn't mean this object doesn't move. It means if this object doesn't move, it will stay. If this object is moving with a constant velocity, it will keep the same velocity all the time. There's no change. These are new parameters we define. So for motion, we have speed. It means how fast an object is moving. For example, 100 kilometers per hour is speed. Velocity is speed and direction. We can say 100 kilometers per hour due north. This is velocity. Acceleration is change in velocity. So if you start from 0 and you end up in 60 miles per hour due north in 7 seconds, you have acceleration. Sometimes we have more than one force. If there are multiple forces, we look at net force. So let's say we have a person, there is F left, and there is a larger F to right. And in this case, when we are looking at Newton's second law, we use net force. It means we subtract these two forces and we find final net force for our formula. So in this case, it will be an average force. This will be a force towards right. But this is Newton's second law. There is Newton's first law. So according to this law, if there is no net force acting on an object, there is no acceleration. If this object is moving with a constant velocity, this object will keep moving with this velocity without any change. If this object is not moving, so it will stay in its position all the time. We also have Newton's law of gravitation. Two objects, let's say we have one object m1 and m2, two masses like the sun and the earth, and their separation is d. In this case, there is gravitational force equal to a constant times m1 times m2, the mass divided by d squared. These forces are equal and opposite, so it means the force between Earth and the Sun is equal and opposite. It's the same force from the Earth to the Sun and from the Sun to the Earth. It's proportional to the mass and it's inversely proportional to a square distance. And this is the same force responsible for orbiting. For orbiting objects, we have this gravitational force, and this object should fall towards another object. Basically, this force is still acting. But what happens when we increase this initial velocity, we can move further away. So small velocity and bigger velocity and so on. And there is a limit. There is a balance. If we shoot this object with this specific velocity, what happens in this case, we have this free fall. Let's say this object is moving in this direction, but we have free fall, so this object will fall toward the Earth. But if you compare the Earth, because we have this round shape, at the same distance, Earth has moved further away. So we have further away surface area from this object. And if we can keep this balance, free fall and moving away, we can stay on an orbit. Actually, Earth is not moving away in this case, it's just the shape. This shape is round, so it looks like we are falling, but we are never reaching the Earth. So this is the orbit. One important point, mass and weight are different. It's very important to keep this in mind. Mass is the amount of matter we have for an object. Weight is the force acting on this object. So you can get rid of weight. For example, if we move one object far away from this gravitational force and there is no other object close to this object, we won't have any weight. In this case, weight is 0. But we still have the mass. So if we define mass as the amount of matter, we still have matter for this object, but weight is 0. Another case is for free-falling object. For free-falling object, let's say an astronaut. Again, in this case, we have mass, but we don't have any way. Because, for example, if we use a scale to measure way, basically this scale is free-falling with this astronaut. And in this case, net force is 0. So be careful, there is difference between mass and weight, but sometimes we use them with the same meaning.